All right, so today's goal is to understand really three words: what a dilation is, or a compression, and also a reflection. We've talked about vertical and horizontal translations, and now we're adding in a few more transformations. So we have the word transformations defined here. Transformation is when a parent function's position or orientation has been changed. And the 2 or 3 new transformations we're adding in today are dilation, compression, reflection. And then down here at the bottom, we have all the 3 or 4 different types of transformations we've studied so far. All right, so let's see these in action. And we're going to graph 3 functions here on this coordinate plane they've given us, but we're going to start with y1 and then y2. y1, of course, is just our parent function. This one should be a piece of cake at this point. So we've got our table of values. We're just taking the square root of these numbers. We cannot take the square root of negative numbers. So anything that's a negative number only, I'm going to put DNE for the parent. But we can take the square root of 0. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And I'm going to graph those points. I may also add in 1 extra point here at the bottom. The square root of 9 is 3. And again, we could fill in these points here, but this is going to be a decimal, and there's nothing wrong with decimals. They're just kind of tricky to graph. So there's our parent. I'm not going to connect the dots. And now I'm going to graph y2. y2 is essentially the same thing as y1, except we have a scalar multiplier out front. So we're taking the square root of the x value and then multiplying by 3. So we've already taken care of the part where we take the square root of these numbers. So the square root of 0 is 0, but then for y2, we're going to multiply that number by 3. Of course, that doesn't change this number. Take the square root of 1, we get 1 times 3 gives us 3. The square root of 4 is 2 times 3 gives us 6. And the square root of 9 is 3 times 3 is 9. And again, the rest of these are still ugly decimals. And we still can't, even if you take the square root of a negative number and then try to multiply by 3, that can't happen. Because taking the square root of the negative number part is where the issue. All right, and then graph those points. The points I have here are 0, 0. I have 1, 3. I have 4, 6. And I have 9, 9. So I have those 4 points graphed, and then I'm going to connect them with a nice smooth curve the best I can. So when we look at the original points and we look at this new graph, we can obviously tell it's been changed quite a bit. The thing you have to watch out for here is you don't say this is a vertical shift. And that's because there's an increase of 2 here, and there's an increase of 4 here, and there's an increase of 3 here. So where a lot of people mess up is they say this is a vertical shift, and that's just not the case. This is a dilation. So we have dilated all of the original y coordinates by 3, thus stretching out the original parent function graph. So let's go ahead and answer question 2 before we graph that last problem here. It says, how did the equation for y2 shift from the parent function of y1? Well, y2 is a stretched out version of y1 by a scale factor of 3. Another way to write that would be to say, usually we use functions, we use f and g. This time they used y2 and y1, but we could say y2 is equal to 3 times y1. And now let's go ahead and graph this last one. And you can probably guess kind of what's going to happen on this last one. We are multiplying all of the original y coordinates by 1/2. So when you take the square root of 0, you get 0, but then you multiply it by 1/2, and you get 0. Let me do it here on the outside so we don't get confused. And then we take the square root of 1 and get 1, multiply that by 1/2, and we get 1/2. So all of the y coordinates are getting cut in half. Square root of 4 is 2, multiplied by 1/2 is 1, and the square root of 9 is 3, times 1/2 is 3/2 or 1.5. So these new points, remember we're going back to the parent function, so the new points are 1, 1/2, 4, 1, and 9, 1.5. So graph those 3 or 4 points, and then you can see what's happened. The graph has been compressed. All of the y coordinates have been scaled back by 1/2. So we can write a rule for dilations of any function. We know this is the general form of a standard function, a times f of x plus h plus k. We've already talked about h and k, but now we're throwing in that multiplier. If the absolute value of a is greater than 1, and we do absolute value because there's slightly different rules when the a value is negative that we're about to finish with. So if the absolute value of a is greater than 1, the parent is dilated. If the absolute value of a is in between 0 and 1, then the parent is compressed. All right, so finally, let's finish with this example. Go ahead and graph y1. So y1, of course, is our parent function. We've graphed that one many times. But now we want to graph y2. And y2 is equal to -1 times the absolute value of x plus 3. So we're doing several things here. We're taking the absolute value of -6, and then we're multiplying that by -1. So the absolute value of -6 is +6, but then we multiply it by -1 and get -6, and then add 3 to get -3. So we're taking the absolute value of all these numbers and then adding 3. Or essentially another way to think about it is we're taking all of these y coordinates, we're multiplying them by -1, and then adding 3. So go ahead and do that. All right, so there's our points. And now go ahead and graph them. So there's our answer in orange. So we can see, obviously, when we multiply by -1, and we talked about this with quadratics, essentially flips it upside down. But really what it's doing is it's reflecting the graph across either, you could say, the x-axis, or it's reflecting it across its own vertex. So that's what we can say for number 5. How did the equation for y2 shift the parent function from y1? Well, it reflected it. I'm going to say across the vertex. and then shift it up 3. Or the other way, you would say y2 is equal to -1 times y1 plus 3. And then finally, this wants us to write a rule for reflections for any function. So we're going to write out all the rules we've discussed all in here in this box here at the bottom. End. So there's all the rules we've talked about as x approaches negative infinity. These three, this left arrow, which is the 3 we've added today.